Boom. Green flow. Good. Hello and welcome back for the fourth time today. For now the section 5.3 fundamental theorem of calculus. This is where the entire course comes together and we understand how these things work together. So fundamental theorem of calculus is going to have two parts. One of them states the formula that I already wrote twice, which is how to compute definite integrals. And the second part of the fundamental theorem of calculus is that ultimate link between differentiation and integration. So part one is to write integral a to b of f of x dx is f of x computed from a to b, which is f of b minus f of a, and you get some number out of it. So this was stated already twice, and here is the third time today. We did a bunch of examples for this, so there's no need to do it one now. What we are interested here mainly is the part two of the theorem. And the part two of the theorem states that the derivative in respect to x of the integral a to x of f of t dt is equal to f of x. This is the part two. First, I'm going to address this f of t dt rather than f of x dx. We call this a dummy variable because I will be plugging variable x as a value when I use this part of when I try to compute the definite integral. So I don't want to plug x into x. So we just change the variables to any other letter and we use t. Now I know this is not an honors section, but this proof is essential for understanding of what's happening here. And this might be actually one of the questions on the honors exam, actually. But this proof is essential. Look at this, guys. I am going to now simply compute this. I'm going to copy the derivative, and we know that the integral of the function is the antiderivative, which is a capital F, which now gets computed from f of a, gets computed from a to x. Now that goes into these brackets because I am yet to take the derivative of it. Now when I plug in the limits using the theorem part 1, I get capital F of x minus capital F of a, and I still have to take the derivative of all of that. Now you remember what capital F of x is. It's the antiderivative of lowercase f of x. Exactly. So the derivative of capital F of x is just f of x. And the derivative, this is going to be a number. What's the derivative of a constant? 0. So the whole thing is f of x. So this is the proof for fundamental theorem of calculus, where we show that if you start with, let's say, sine t, you are going to end with sine x. It's just a swap of variable because of the fact that we will be plugging this in. So you don't want to have over here f of x and then plug x. Right? That's weird. So we start with f of t, you get f of t, and then you plug x, you get f of x minus f of a. This is a function whose whose derivative. So you're taking derivative of antiderivative. They cancel out, right? And you just get the original function back. Minus this is a number, so derivative of a number is 0. And then you get f of x minus 0 is f of x. And you got it. So now I'm going to do an example of this. And then I'm also going to do the short version of this. So say you have d dx of integral, I don't know, 2 to x of x squared plus cosine x. Sorry, t squared cosine t dt. You should already know the answer just by looking at this. What is the answer? If you started with f of t and you ended up with f of x, what's the answer? That's the input function. What's the output? It's x squared plus cosine x. Right? You get the same function back. So let's see. I have the derivative. This becomes t cubed over 3 plus sine t computed from 2 to x. I will plug these values in and get x cubed over 3 plus sine x minus 8 over 3 minus sine of 2. Sine of 2 radians, that's almost like, I don't know, 2 pi over 3. Say, something like that. So you can actually punch this in a calculator, put your calculator in radians, and just write sine of 2, and you will get the value of it in decimals. So now I need to take derivative of this. When I take derivative of x cubed, I get 3x squared over 3. These guys will cancel. Derivative of sine is cosine, and then minus 0 minus 0. The answer is x squared plus cosine x. Done. So we started with t squared plus cosine t. We ended up with x squared plus cosine.
So it's the same thing, just you take out the t and replace it with that?
Yes, but what happened in between? What happened in between, guys, is that you integrated and differentiated, and you are supposed to see now that those two operations cancel each other out. You are used to that with your calculations. You know that you can solve equation x plus 2 equals to 0 by using the opposite operation of subtract 2 on both sides. You know that you can solve 5x equals to 9 by dividing both sides by 5 because that's opposite operation. You know that you have x squared equals to 9, you can square root both sides because that's opposite. And e and ln are opposite, and you constantly use these opposite things to solve equations and to do things, right? One way you do it, the other way undoes it, right? So do, undo, do, undo. Same pairing happens with operators, differentiation and integral. They're opposites of each other. So if I say that the integral of 2x dx is equal to x squared plus c, I can say that the derivative of x squared plus c is equal to 2x. And we know it is because the derivative of plus c is 0. So going one way or going the other way, we flip-flop between same functions. So technically, what have we done here? We integrated, and then we differentiated. And we came back to the same point. This is the equivalent for operators like you have maybe for functions in terms of inverses. You inverse the function and you inverse the function again. So you go from e to the x to ln x back to e to the x. So if you are looking for understanding of calculus, you will study this section and you will try to understand how and why, and look at the proof closely, how and why derivative and integral are complete opposites of each other and undo each other. If you are concerned with making it through the section, all you need to do is to replace t's with x's. That's the bottom line. So that's how it goes. And now I would like to challenge you. This is the end of this section, so I just want to challenge you with a question. Why are these two opposites of each other? You've seen their definitions, you've seen what they do, you've seen many derivatives taken and many integrals taken. The ultimate question is, why are they opposite? So why is the derivative completely opposite of integral? Formulate, okay, fine. The derivative at the point is the slope, but the derivative is a function, actually, which generates slopes. It's not what I'm looking for, but it was a noble attempt. You still need to formulate the... I'm sorry? Nope.
Well, what's the rate of change? So, like, you have the tangent line going down, right, cutting through the formula, and then...
It's not... doesn't contain tangent line.
It's with rates of changes. Is it because the rate of change and the area underneath the curve are like... Because it does generate the function, and then the integral finds the area underneath that function. What?
All right, so who's going to tell me the definition for the derivative? What's the definition for the derivative?
No.
What's the limit definition? Come on, let's go.
Yeah. You're in it. Write it out. Yeah. All right, you're in it out. And then I'll try. Now read it off the paper. H.
All right. And what was the definition for the integral? Well, I should have used a's here, right? Yeah. You wanted the slope. I don't have to, but whatever. Does anyone see it? Okay, 0 and infinity. What happened? I can't hear you.
What's the initialization term under the sigma?
I equals 1. All right, so you said h goes to 0, n goes to infinity. Fine. Anything else?
Is it like the correlation? Yeah, right.
It is literally that easy. Sum, okay. And the other one is? That's a wrong word to use, but we'll use that one as well. Could use change maybe, but just cow.
Cow.
Just throw in a word.
Yeah.
Bananas. Okay, so we all see the 0 and the infinity, right? Now, you said sum, but if I circle the sum, what do I get to circle up there?
Like yourself. There you go.
Every time without the fail when I get excited.
You just can't be happy while doing this. It's not allowed. Yeah. The gods of mathematics are frowned.
Yes. So look, this is that. What's different? And the answer is everything is different. Everything is different. Look, this is 0 and infinity. This one has a subtraction. This one is adding. This one is dividing. This one is multiplying. Everything is opposite. Everything is opposite. They are completely opposite of each other. Do we see that?
Let's go one step deeper. What does that mean in like physical applications?
Well,
Like the car movie.
yes. So the derivatives in physical application will show the change. So how do you go from being, 30 pounds, 60 pounds? All right? So the change. Give her some time and burger. Now, the integral shows accumulation. So if I want to calculate how fast I'm going to take a look at the derivative because it will show me instantaneous change. But if I want to see how far I went, that's accumulation, and it's going to be calculated through integral.
It's actually hella cool.
What?
Hella cool.
Of course it is. It's math. It's lots of fun.
I remember I took Calc 1 before I took any physics classes, and does that mean I get the whole class?
Yes, because, all right, so this is it for this one. I'll explain that about physics now, but there is nothing else to teach in this section. We are done with this. You have this proof, right? And this could be on the honors exam to actually do this proof, to prove the formula and how and why it works. Other than this, guys, on your for our exam, you must know both formulas. You better know part 1 to compute a whole bunch of problems, and then part 2 is technically yours changing t's with x's, right? And those of you interested in mathematics who are going to push through, right, more courses and so on, you might want to know why. Okay, so that's it. We're going to take a short break and then end with those few formulas from 5.4, technically almost ending the course.